Yeah, thank you very much. I'd like to start with thanking the organizer for organizing this wonderful workshop, but this time I really mean it. It's really a wonderful it's really the wonderful gathering, and to see so many people join. And so I will start with a discussion of SPT order and algebraic topology, but I have to warn you, I don't know what is algebraic topology. So it's a physicist way, something like algebraic topology. And so first, let me just make a remark that in physics we study quantum theory, but there are two versions of quantum theory. And so when we want to study things more carefully, like classification, we have to say which quantum theory you are using. And these two quantum theories are different, so there should be two separate theory here. And so first quantum theory I call the H-type quantum theory. It means quantum theory which have a Hamiltonian, which have a Hilbert space. So let me see. Yeah. So we have the Hilbert space, which have a tensor product structure, and we have a Hamiltonian operator act on the Hilbert space. So that's define some kind of quantum system. And there's another type of quantum theory called the L type. So it's gone. So the L type theory is L type theory is really, this L really for the Lagrangian. It's really defined via so-called Lagrangian path integral. So therefore, this theory is well defined for the space-time manifold of arbitrary topology. But however, for the H-type, the space-time manifold have some restrictions. So these are two different theories. So if I want to consider classification, and then I have to specify which type theory. And so in this talk, I will mainly talk about L-type theory. This L-type theory is closer to some mathematical formulation. But certainly in kinematic physics, we are more interested in the H-type theory. And as a distinction, so for example, there's a E8 bosonic quantum Hall states, which we call which is really a H-type theory. But however, such theory, I think at the moment they do not exist as L-type theory, and we have to have a 3-layer of E8 states stacking together to make this a valid L-type theory. So I will come back to this point. So what is L-type theory? So L-type theory is defined using following data. First, we have a space-time manifold, which dimension D. And we have a triangulation on the space-time manifold. Okay. And then for every simplex, we associate with a few tensors. So then before the tensor, we actually, on every simplex, we have labels. Actually, on vertex, we have label. On the edge, we have label. On the face, we have labels. So those labels are degree freedoms. Okay. And then because we have labels, then associated with every simplex, we can have tensors. For example, for the 3-dimensional example, for the tetrahedron, we can have this tensor C with this with the E is an index on the edge, V is index on the vertex, and the phi is index on the face. Okay, so we have and then certainly we also have a tensor on the edge and a tensor on the vertex, and etc. So, okay, those tensors in general could depend on some kind of a connection. So basically, because we have manifold, you can imagine we have SON connections, and then this SON connection. So on edge, you may imagine we can have SON connection on the edge, which is described as some kind of SO transformation. So those tensors may depend on those SO transformation in general. Okay. So this basically is a data which define a so-called L-type theory. Okay. And certainly, there's usually in quantum physics, we have a so-called unitary theory. And it's in this general formulation, it's a little bit hard for me to specify what is a sufficient and necessary condition for the unitarity. But here, it looks like we have a sufficient condition. This is at least a sufficient condition for unitarity. And there's a few subtleties that this triangulation have a so-called a branching structure. The branching structure basically is that on every edge you have an arrow. But on every triangle, the arrow are frustrated. Basically, we don't have a loop of arrow. Okay, so that's kind of branching structure. And when you have a branching structure, the vertex on the every simplex are really ordered. So there's 0, 1, 2, 3. That's ordered. So 0 have no incoming edge. 1 have 1 incoming edge. 2 have 2 incoming edges. 3 have a 3 incoming edge, and etc. So that's the way we can order all the vertex. And also,
what happened to two simplices? You have like data to 1.
Yeah, in general, you could have two simplices. Yeah, in this case, but I skipped that because when you have a triangulation, every two simplexes is shared by precisely 2 3 simplices. Because of this, you can take square root of a tensor on the 2 simplices and absorb that into this tensor in 3 simplices. But you cannot do so for the edge. That's a very good question. Because for the edge, it's maybe shared by 2, maybe not 2, maybe 3 or 4 or more 3 simplices. So it's hard to absorb. But the 2 simplices can always be absorbed. So we skip that. Yeah. But in general, you could put in there. Yeah. And and because of the yeah.
You need to tell us what the vector spaces are that these tensors operate on.
Those are just complex tensor. These two are real tensor, which is positive. This is the one defined on the vertex. On the edge, they're kind of some weights, some kind of weighting factor. But the C is in general is complex tensor. So here I don't define vector space because this is L-type theory. So we have a label. There's no Hamiltonian. There's no vector space. We just have path integral. I try to define a path integral here.
But what should I think that the indices run over in arbitrary?
Oh yeah, there's some range. So each index is running over a certain range, some finite range.
Some finite set.
Some finite set.
So there's a tensor and some tensor products.
They are all finite dimensional tensor. Okay. Yeah. And because of branching structure, there's 2 kind of 3 simplex, plus orientation and minus orientation. On these 2 different 3 simplex with different orientation, we have 2 different tensors, C plus, C minus assigned to these 2 simplex, but they differ by some complex conjugate. So this is a sufficient condition for the unitarity. So this actually defines a L-type quantum system. And this, I don't know, this may not be most general, but at least it's a wonderful working definition. So this is our enemy. So we try to understand the behavior of this kind of a system. And so once you have the system, then you can compute something so-called measurable quantity. But certain measurable only means does not necessarily means measurable in the laboratory, but measurable in numerical computation at least. And so one thing is a so-called partition function. Basically, you just multiply all these tensor on the edge, on the vertex edge, and the tetrahedron, etc. together, and whenever you have a shared edge, a shared vertex, etc., we sum over the index on those shared edge and the vertex. Okay. So this gives us a complex number. So this complex number is a partition function. But from the partition function, we can also define so-called correlation function. That is, we can just modify a tensor from T to T cubed in general. Just modify the tensor on some simplex, and then we compute a new partition function for this with this particular multiplication, Okay, then we divide the previous partition function before multiplication. So this is the correlation function of this modified tensor, basically. And this is where this formulation is linked to physical experiments, because the experiments can measure all these correlation functions. And so basically, once you have a physical model like this, L-type model like that, you can compute the correlation function and perform neutron scattering experiments, and you can really measure those correlation functions. And with this, now we can define so-called short-range correlated system. And this is the main topic of this talk. The short-range correlated system are simple and relate to topology. So, but what is a short-range correlated system? A short-range correlated system, this concept exists only for infinite system. This do not exist for finite system. So we have to consider so-called infinite system. And like what the mathematicians usually do, the infinite system usually is not a single system, but a sequence of systems whose size go to infinity. So in this case, what we do here is that we take a space-time manifold whose size of space-time manifold go to infinity. So space-time getting bigger and bigger. And but the size of simplex is order 1, always order 1. So we have a more and more triangulation become finer, but space-time getting bigger, but the simplex size about the same. Okay. So that's how we take this limit. And also we have this limit that each vertex is shared only by a finite number of simplexes. So we don't want to have a very weird triangulation. And so there's some kind of uniformity here. So every vertex only have a shared finite number of neighbors. Okay. And so using this definition of infinite system, then we can define the short-range correlated infinite system. So some infinite system are short-range correlated. If this irreducible correlation function, so this kind of irreducible correlation function, have an exponential decay, and for every system in this sequence, and so this formula holds uniformly for every system in the sequence, and with a fixed C, so the correlation length is fixed, and so this basically defines this short-range. This first property is the short-range correlation. But however, there's another important property that because here we consider the sequence of system, and it's possible that the different system in the sequence are totally different. So for this side is quantum Hall state. For the other side is Tor code. Then next side is maybe is a topological insulator. So we didn't specify such condition. So they all satisfy this. So there's another condition that all the system in the sequence should be related. They should be similar. So this is this condition is that because the system in the different system in the sequence have different size, so we can always add actual degree freedom, which is a frozen. We don't do anything, just a frozen fixed, and so that the smaller system with this additional frozen degree freedom would have same degree freedom as a larger system. Then we say the larger, then this combined system can smoothly deform into larger system without destroying this short-range correlation property. So this will link these two systems with different size. Yes?
So when you first said this, I was assuming that as you increase the number of cells, you're keeping the same kind of structure of tensors and stuff like that on the cells. And then as a physicist, I would have thought that then it kind of follows that there's a smooth limit for the behavior of the system, because I'm imagining that you're sort of somehow keeping it until you're the same. Is that not?
Yeah, it's more like, actually, this is at the moment it's my best trial, and it could still be wishful thinking. What I'm really trying to say is I didn't specify the triangulation structure. So maybe in one side it's a square lattice, on the next side is a triangular lattice. And even for the same tensor, there could be different phase. So there are all sorts of problems. So actually, I'm not sure what I described makes sense or not. But however, the difficulty is that we try to take a thermodynamic limit. without assuming translation invariance. And that makes things very difficult. When you don't have translation invariance, things, how to take some alignment without translation symmetry is became difficult. So that's here is my attempt try to overcome this difficulty. So this is a kind of proposal. And so this is also very important because when you have a smaller system plus some kind of degree of freedom which are frozen, and then the smaller system will be equivalent to the larger system and the deformation without destroying this short-range correlation property. Then we can say that the system with different size are similar. So then this whole sequence may describe similar system. Yes?
So it looks here like you're changing the dimension, like you're adding in a new degree of freedom.
Yes.
So are you changing the manifold you're working in?
No, I didn't change the manifold. So basically, what I did here is for the triangulation is that, remember when I have a triangulation, we have some index here. For example, I have a E1, 1, 2, E0, 1, for example. For example, we have some index here. And then we just add some index like E4, 5, E6, 7, we just add some actual index. But at the beginning, these actual indexes are frozen. They're always equal to 1. They don't change anything. And then later, when we do deformation, then we allow those actual index to be able to change, and we can design new tensor which couple those index together, And then you try to deform. So basically, it's a way to refine the triangulation. When you refine triangulation, you introduce actual degree freedom. But then there's a process. There's a way to deform a tensor so that the tensor can be deformed from a previous triangulation to a new triangulation. So one can imagine, I didn't describe this in detail here. You can imagine there is a way to make tensor to deform continuously. And I try to say that during this tensor deformation, this short-range correlation property is not changed during the whole process of correlation. So this really kind of tie everything together. Yes?
So is it correct to say that if you were talking about H-type theories, the language you'd use is deformation without closing the gap?
Exactly. Yeah, since I try not to say gap, I just say short-range correlation. Yeah, indeed. So without closing gap. But this picture is an H-type picture I copied from another paper. Usually I don't talk about L-type. Anyway, and so this basically define. So the previous transparency I defined this so-called L-type system. Now I define so-called short-range correlated infinite system of L-type. Okay, and so this is the subject you want to study. And then next we can define so-called a phase. So in previous transparency, I only define a short-range correlated infinite system. It's a one system. That's already a sequence of system actually. But now we can define the phase. Phase actually is the equivalence relation between equivalence class of this so-called short-range correlated infinite system. So there's an equivalent class, there's an equivalence relation. Here, at this stage is easy to define. So the equivalence relation is actually, suppose you have two sequences of a system, which is this short-range correlated infinite system. Okay, and we just say that if among two sequences you can deform a tensor from one system to another without destroying this short-range correlation property, then the two systems are the same, are in the same phase. So therefore, we just described that we can deform tensor from here to here without destroying the short-range correlation property. And also here we say between two different systems, between two different sequences, we can deform tensor from here to here without destroying the short-range correlation property. And so basically, among those two systems, we can deform tensor among any of those subsystems, which is a system which we don't destroy the short-range correlation property. So that's basically a defined short-range correlated phase. And this is the topic actually, So the question is, when using this equivalence relation to define the equivalence class of this Schrödinger correlated phase, so how to classify those? So what is the mathematical foundation, mathematical language for this kind of object? And so apparently some kind of higher category theory is involved, and it's maybe some kind of higher category theory happen to describe this kind of a classification of this kind of object. And so this really defines so-called Schrödinger correlated liquid phase. And here let me just explain what I mean by liquid. Liquid really means this step, that the system with a smaller size, the system with bigger size, can deform each other if we add some frozen degree freedom. So basically, liquid means a system can dissolve product states, can dissolve a frozen degree freedom arbitrarily to make its size getting bigger and bigger. And so this property make it a liquid. And because this property, certain well-known states, for example, like Haas cubic code, which is also a gapped state, and I think that Haas cubic code is not a liquid, so this condition is not satisfied. We think we don't have proof, but we think maybe that's what happened here. And then for the symmetry, symmetry in this language, symmetry is very easy to add. And basically, we have a symmetry group first, and then we say that the index admit a symmetry action. So therefore, the group element can act on the index to get a mapping between this index. Okay. Then the tensor is invariant under this kind of mapping. And so when the tensor satisfies this property, we say, okay, this is an L-type quantum system with a symmetry described by symmetry group, and that's it. And but however, when you have a symmetry, the equivalence relation became a little bit tricky. That is, when we deform a system from one to another, we have to assume that during the whole deformation path, this symmetry condition is satisfied. Okay. So therefore, when you consider a system with a symmetry, when you describe a phase with a symmetry, the equivalence relation getting smaller because we require the deformation path to satisfy the symmetry condition. So therefore, because the equivalent class getting smaller, so maybe you have a more equivalent class. So there's maybe more phases. So when you have a symmetry. So therefore, in this talk, what we try to do here is try to understand this Schrödinger correlated liquid phase with a symmetry or without symmetry, and etc. And I think the next talk by Zheng may talk about this Schrödinger correlated phase with symmetry. Yeah. Okay, that's my first part. And so if any question, we can ask here. Yeah.
So, if I think of the system, I mean, these are probably some kind of Wick-rotated systems where time has been rotated. But if I go back to the real time, can I think of having L-type as opposed to H-type as saying that the system has relativistic invariance?
Yeah, this is a very tough question. And so because for the Minkowski space, for the real time, we don't even know how to discretize space-time lattice. I think that's my understanding. So to formulate a lattice theory for space-time, at the moment, I think we only know how to do it for the Euclidean space-time, not for Minkowski space-time. The reason is that in the Minkowski space-time, there's a light count plane which have zero distance among them. And so there's all kind of theory called the causal set or something, and trying to do that, and I tried to learn that. It became very complicated, so I kind of gave up. So therefore, I try to say that in condensed matter, we only do the partition function with imaginary time. So we only consider Euclidean space-time.
But if we think of the low energy theory and we approximate that by field theory, a continuous field theory, then whether it's gapped or not, do you expect that field theory to have relativistic invariance or not?
Actually, that's a very interesting issue, and the answer is almost yes. That is so here I consider state with Xiao-Gang correlation. Imagine there's some tensor, some other choice of tensor, which actually the correlation is not Xiao-Gang, have algebraic decay. And amazingly, at least from the experience of kinetic matter physics, most systems with a Xiao-Gang correlation, with gapless, with algebraic correlation function, have in some sense a Lorentz invariance. Means the velocity is finite, the speed is finite. It's the dispersion relation we call the linear dispersion relation. The speed of light may not be the same. Maybe the different part of theory have a different speed of light. But there are linear dispersion relations. So somehow linear dispersion relation is emergent.
No, but it's kind of accidental thing. It's accidental thing.
May not be accidental. That's more than accidental. Like a solid, piece of solid. All the solid, the phonon have linear dispersion relation regardless what atom form the solid. So this is quite impressive. Why nature, whenever it's gapless, want to have linear dispersion relation rather than quadratic, cubic? Why linear or any other exponent?
Magnet has a quadratic.
Yeah, exactly.
What?
Magnets and ferromagnet have a quadratic dispersion relation.
Yeah, there are systems with a quadratic, but I try to say the most there's like a superfluid, solid, seems the linear dispersion just appear more frequently.
Also, linear dispersion, okay, you can have several different modes with different speeds of light.
Yeah, that's right. So that's breakthrough, but it's still exactly. But still linear. That's what I try to emphasize. Yeah, it's not Lorentz invariance. Yeah, that's right. Yes.
So, if I do a reverse process of going from, say, bigger system to smaller system by freezing out something, so I have some D sides, and I try to freeze some arbitrary one of them to one side and try to get back a smaller system. And in that process, sometimes I can get a different manifold. Suppose I have a plane and by freezing things, I can create punctures and get some torus or something.
I don't quite know what you're talking about.
And that is the process where you're defining thermodynamically a sequence of things. Suppose I go in the other direction, so
yeah,
smaller.
Yeah.
And then I try to freeze something by I freeze some arbitrary few sides, for example, and I try to get a slightly smaller dimensions. But in that process, sometimes I will think freezing is almost like sometimes creating a puncture in the system.
I see.
You can change the manifold. For example, you can go from a cylinder to torus, and you can do all kinds of.
Yeah. So right now, right now, you can certainly go both ways, become bigger or smaller, and but we don't want to go so far. Means suppose we have a system with a million triangle. I want to reduce to 1,000. I don't want to reduce to a few, because when you have a few, the things is it's hard to view this as a thermodynamical limit. Anyway, okay, yeah.
Can you expand a little bit more about so the difference between the H type and the L type classifications? So, I mean, if I view my H type theory as something where I could take my Hamiltonian and then quick rotate and compute a partition function in imaginary time, and that was an okay way to treat it, then I would get an L tape.
That's right. But however, that L type theory, that's passively only defined on the space-time, which is like S1 times the space manifold. But however, you may not be able to define that theory on arbitrary space-time manifold. So the example I try to give is that for the E8 quantum Hall states, maybe the example of that. That you can define E8 quantum Hall states on the space-time manifold, which is S1 times the space manifold. But one may have difficulty to define E8 quantum Hall states on arbitrary space-time manifold. Basically, I try to say that E8 quantum Hall states have anomaly as L-type theory. So they don't exist as L-type theory. Basically, if you're using the tensor I just described, you never produce E8 quantum Hall states. And that's a claim. So, but somehow, if you there's a H-type theory, you can certainly produce E8 quantum Hall state for L-type theory, for H-type theory. Yeah.
So do you believe that L-type theories are contained in the set of H-type?
Yes. So every L-type theory can be viewed as H-type theory, but not every H-type theory can be viewed as L-type theory. And also, a distinct L-type phase may be the same H-type phase because H-type is more general. So this is just so that's to make a classification a little bit different. Yeah. Yeah.
So if you go back 2 or 3 slides where you wrote down what you call it. Yeah, that one. So I mean, that looks kind of like a toroidal zero.
Exactly. Yeah, it's really trivial. Yeah, and so for trivial, and one have this so-called fixed point tensor. But later I will discuss. So this is really a trivial state sum. So I should say state sum. So this is really a L-type theory are kind of state sum theory.
So the trivial is much more special.
The difference is that this is more general trivial is that this tensor may depend on the connections. And I think that may be needed to produce a theory like this E8 cube. I think E8 cube can be produced. But that you probably can't. I mean, this the theory with non-zero chiral central charge probably require this tensor to depend on the space-time connection. In the trivial state sum, the tensor do not depend on space-time connection, so you only get central charge equal to 0 states in 2+1 dimension.
But also in trivial, you have variables which live on.
Yeah, but this is kind of
the constraint, right?
Yeah.
It's a constraint coming from the algebra structure.
Yeah.
But here they're just some overall.
But this indeed this I should say that this you should view this as generalization of state sum formulation, which are familiar to mathematicians. So those are kind of generalization of the state sum formulation.
It's more like some generalized Ising model.
Yeah, that's also like that. Yes. Yes.
Yeah. So you mentioned in the H-type definition you need the Cooper space to have a tensor product structure. But if I impose the gauge condition, for example, Gauss law for gauge theory Cooper space, then you lose that tensor product structure of the Cooper space.
Yeah, right now we don't impose anything like that. And so basically, there's no gauge constraint. There's no Gauss's law. And so the Gauss law just maybe all energy penalty. So they are not strictly imposed. So there's no. So all this degree freedom are independent. They can. So this sum, all the degree freedom are sum independently. So without any constraint.
So if I impose that constraint strictly, would that give you more?
We'll make change, but we don't need to because that constraint can be imposed by say some certain tensor are 0. If a certain tensor are 0, that means those pattern index don't appear. They have 0 contribution. So therefore, in this case, we don't need to do that. Yeah. Okay. And so let me just so to make a classification is very difficult. So we try to make things simple, and so one way to make things simple is to consider a theory with a symmetry. But without symmetry, we know that we have this. Let me see. Let me skip something. Oh yeah, I skipped something. Okay. So there's a trivial thing. So let me just give some 2 examples. A trivial L-type theory is this. It's just the tensor is non-zero only when all the index equal to 1. So basically, every other value index tensor equal to 0. Only when all the index equal to 1, the tensor is non-zero. And this non-zero value can be the W0 for the tensor on the vertex, the W1 for the tensor on the edge, and the W3 for the tensor on the tetrahedron. Okay. And then the partition function just equal to this weight factor raised by power of a number for 0 simplex, 1 simplex, 3 simplex, and etc. Okay. And this you can show that a different choice of a W all belong to the same phase because you can change the W and keep soldering correlation problem with no problem. Okay. So this kind of phase is called the trivial topological order. Okay. And there's another example is that all the index on the edge and the phase are equal to 1. Tensor non-zero only when all the edge index and phase index equal to 1. But however, the vertex index can be any value. We can assume the vertex index, say, take a value in a group, for example, a discrete group. And then the tensor actually do not depend on the value of vertex index, so they're all equal. So no matter how you choose different vertex index, they're all equal. Okay, in this case, the partition function is something like that. So there's a, because the vertex index can run over this order of a group, so there's extra power from number of vertex. It turns out that, so this is another example. They also short-range correlated. It turns out that these two are kind of related in the sense that they are in the same phase. Basically, we can deform the tensor of this type to this type, and so without destroying the short-range correlation property. So, so these two belong to the same phase. And also, you can see that on this trivial phase, there's a special case where all the weights W1, W0, and etc. all equal to 1. So the partition function equal to 1 for arbitrary space-time manifold. Okay. So this led to this conjecture. That is, if the partition function is equal to 1 for arbitrary orientable space manifold, then such a system must have a trivial topology order. Okay, so certain this example satisfies this, but here I try to say for any system which have this property will belong to same phase. They are equivalent to this particular trivial setup. Okay. Yeah.
Defining topological order. How are you defining topological?
Yeah. So that's the next one.
Okay.
So last one just define trivial one. So this trivial is this. Trivial topology is this phase. But however, not every short-range correlated system are connected to trivial one. And those are so-called topological order. So basically, a non-trivial short-range correlated system is called a topological ordered. So
how did you define trivial topological?
Trivial one, previous slides. That is
examples in the conjecture. Like,
yes.
How did you have a conjecture that all such things
are trivial? Yes.
Are trivial.
Exactly. So the conjecture is that if partition function all equal to 1, then this kind of tensor can continuously deform into this kind of tensor without destroy the short-range correlation property.
Okay, so example one is like a definition of a phase.
Yeah, example one is a particular example of a trivial topology order.
Okay.
And this conjecture says any system with property would belong to this phase.
Trivial topological order is the equivalence class of that example one.
Exactly. That's a more general definition. So actually this one, even this is not satisfied. There are some trivial topology which do not satisfy this property. This is sufficient property, not necessary. So this yeah. But however, there are systems which are not connected to the trivial one, which during the deformation you must lose short-range correlation property somewhere. So this is that's really a topology order. And then this and then for the system with the symmetry, as I mentioned, that then we may have more phase. Okay, but with this understanding, there's a way to understand the phase with the symmetry in terms of phase without symmetry. It means by which I mean that if you remove the symmetry, you know, for those kind of phase, if you remove the symmetry, then all these phase all became the same trivial phase. Ignore the symmetry. If you allow the deformation to break the symmetry, then they all can those are all can be connected to this trivial phase. However, if the deformation must satisfy the symmetry, then you'll find that there's a different class here. So those seems the simplest. So the system with the symmetry, but however, if you ignore the symmetry during the deformation, they all become trivial. So those are simplest system. So maybe we can make some theory out of it for this simple theory. So this simple theory is called the SPT states, okay, and which is now become very popular. Is there's a topology insulator and Holden phase, etc. They are example. It is SPT phase. Okay, so right now we try to in the next we try to develop a theory for this SPT phase. Yes.
What are G1 and G2 in these diagrams?
Oh, just some parameter in the tensor. The G1, G2, you know, that's usually physics the way to draw the phase diagram. The tensor depends on some parameter like magnetic field, pressure, and then when you're changing these parameters, the tensor changes, and you may get a different phase. So those are parameterized tensors. Yeah.
I want to actually the previous definition was trivial topological orders that the partition function takes the absolute value like a norm to be one or just any one phase.
No, no. The statement is following. If the system have this property, then they have a trivial topology order. This is just a sufficient condition. I don't want to use this as a definition of a trivial topology order, because trivial topology may not satisfy this property. Just if this property holds, it's sure it's trivial topology order. But even that is a conjecture. Okay, so with all this preparation, I don't think I have much time. Only okay.
30 minutes still.
Okay, yeah. But I only just started. Okay, so
just ask, when did topological invariance slip into the discussion?
Later.
This is non-relativistic.
But if it's later, then I don't understand why you're making a conjecture about the partition function being 1 for every topological manifold.
No, it says if you have a tensor which have this kind of partition function 1 for all closed Orient manifold, if the tensor have this property, then that tensor must describe a trivial phase.
Are you implicitly assuming that Z is a function of the topology of the manifold?
Yes.
No, wait. So here actually, we think all closed manifolds.
Yeah, they're all closed
They
manifold.
also mean like arbitrary triangulation. So something.
Also arbitrary triangulation. There's a lot of
Does
going
it
to.
imply that you get the same Z if you have 2 different triangulations on the same manifold?
That's right. So the tensor should satisfy the property that is triangulation independent.
Oh, have you said that?
No, this suppose you have a tensor. So this means this equal to if.
That's a very small.
Yeah, maybe I should say more precise. If this I should have a more standard mathematical language for this. I mean, if a system have this property, then it's trivial. Yeah, but that's for very, very special tensor.
But
Yeah.
also some of the definition of topological order involves invariance and the change of triangulation. Because the way it was defined
It's a little bit tricky. Yeah,
included
yeah.
so the invariance and the change of triangulation.
Well, all that was invariant under change of triangulation was the gap didn't close to a particular value of the partition function.
No, that's true. Yeah, but I'm just saying
But so I'm confused when you're, well, I'm just confused when you are assuming topological invariance and when you're not.
Yeah, topological invariance is a little tricky. Yeah, but that's later. But let me, since you raised this question, so let me just give an example, like this E8 quantum Hall states or E8 cube quantum Hall states. The partition function actually is e to the integration of a gravitational transformation term.
Yeah.
And this is not topological invariant. It depends on the metric. But somehow even this non-topological invariance is regarded in some sense as topological invariant. I don't know in which sense, but maybe later I'll try to see I can address. But for some system like Tor code, then indeed the triangulation invariant tensor would give a topological invariance in the usual sense. But for the E8 quantum Hall states, things are more complicated. And here, my discussion include E8 quantum Hall states, all this chiral theory. Okay, so it turns out that this simple the thing which can reduce to trivial case is called SPT. These SPTs have a theory. This theory is this so-called group cohomology theory. So let me just describe where this how group cohomology enter into the game. But with the setup, with all this setup in the previous half an hour or so, then it became very simple. Actually, this question became very simple. Because I already say that this SPT phase must have a trivial topology order. So to have an example of SPT phase, we just want to have an example of a tensor such that the partition function equal to 1 on any closed-oriented manifold. We just need to find those tensors, find some example of those tensors. And those tensors have a symmetry. Suppose this tensor also have a symmetry. Some tensor with a symmetry also satisfy this condition. If you find an example of that, then that's an example of SPT states. And that's all I do here. And this example happens to be group cocycle, basically. And for those who know group cocycle, group directly give you this example. But let me just describe this a little more carefully. And now we'll reduce the dimension from 3 to 2. So 2 is easy to draw. So here is a triangulation of a space. Okay, so that's all kinds of triangles. And then on every vertex, I have a weight. Okay, and on every triangle, we have a tensor. But this tensor I call the nu2. Okay. And the index, we only have index on the vertex. Index on the edge are all equal to 1. So we can ignore the index on the edge. We only have index on the vertex. That's again another simplification. And index on the vertex is given by the group element. So this index on the vertex is given by group element. Okay. And so then the tensor on the vertex, which is just this vector actually, is all equal to 1 over number of group element. Just some weight is 1 over group element. And then then we have some tensor on the triangle, which depend on the 3 index on the vertex of triangle. That's a 3 index. Okay. Then we have 2 orientation triangle plus 1 and minus 1. You can see this arrow goes this way. That's plus. The arrow, this 2 dominant arrow go that way. So that's minus. So on the plus, we get a nu. On the minus, you get a nu star. So 1 on the nu star, just this different orientation have nu or nu star on these 2 triangles. So this actually define a L-type system. And in physics, we call this a nonlinear sigma model. There's again a strange name. Nonlinear sigma model really means we only have index on the vertex, no other index. Specific physics is a way to say nonlinear sigma model really means that. Okay, and so certainly the symmetry condition would be that this tensor is invariant under the symmetry transformation. So that's this tensor should have some symmetry condition. So then we need we want to find a tensor such that this tensor have this condition that the partition function on space-time with arbitrary topology all equal to 1. Can we find a tensor which have this property? So basically that's a question. And the answer is yes. And first we try to find a tensor such that its a partition function equal to not partition function, the product of a tensor without summing over the index, just a product of tensor, all equal to 1 on any sphere before we sum it. Okay, before we sum it, we first need to find the tensor on every sphere, the product tensor all equal to 1. Then certainly, the simplest sphere is a tetrahedral. So we have with 4 triangles. So that means we need to find a tensor whose product equal to 1 before we summing over the index. And because of this, we assume this tensor is a pure U1 phase, so the complex conjugation and the inverse is the same. So I write this in this way. And this became well-known cocycle condition. So actually, the tensor satisfies this algebraic equation, and the symmetry condition. This symmetry condition and the algebraic equation is called a cocycle. That's it. So that's group cohomology theory in 2 transparency. And so we just find this when this tensor then naturally you'll find this then at least the partition function every sphere all equal to 1. Okay, once you have this tensor. Okay. However, the solution, this equation have many solutions. If you find one solution, then you can construct another solution by including this kind of phase factor, where beta 1 is some phase factor dependent on 2 index G1, G2. Like beta 1 living here is a phase factor dependent on G1, G2. But some arbitrary phase factor will depend on G1, G2. Then once you have this kind of phase factor, you can using the phase factor on the 3 edge of a triangle to modify the tensor on the triangle in this fashion, and you find that then it's a mu2 tilt is also a solution for that. So then in this case, we say these two mu2 tilt mu2 are equivalent. If they differ by this kind of phase factor, we say they are equivalent. Then the equivalence class of this solution will be called this group cohomology class. So that's basically the group cohomology. Okay, and so this group cohomology have a very special property that some probably already mentioned that it's a retriangulation invariant. So basically, for example, the evaluation partition function do not depend on how we triangulate the space-time manifold. If we choose our tensor to be cocycles, for example, consider a part of a triangulation. We have the two triangles like this. Then what's the product two tensor will be on this triangle have this product, these two tensor here. If we retriangulate these diamonds, then we have two different triangles, then we have two different tensor enter here. It turns out that product these two tensor and product these two tensor is the same, because this relation, if you move all tensor to the other side, is the same as this previous cocycle condition. Similarly, we can add a point to the center of this triangle to make this triangle into three triangles. It turns out that the product of three tensor for these three triangles is the same as the tensor for this one triangle. And again, moving this tensor to the other side is reduced to the same cocycle condition. So therefore this evaluation partition function do not depend on triangulation. So you can using any triangulation to evaluate partition function. So this is really notion for so-called in physics called the renormalization group fixed point. So the group cocycle are RG fixed point. So they are independent of triangulation. You can make a cross graining, get the same partition function. Okay, and then using this property, we can show that the partition function equal to 1 not only on the sphere, but also on any space-time manifold. But I'm not sure really any, but anything. What I say is on any manifold which can be obtained by gluing spheres. That's the only thing I can say. I don't know whether certainly in 2 dimensions we can get any manifold. In higher dimension, maybe there is something I heard called handled construction or handled body construction or something that may be related to this. But anyway, this example, we can glue this another circle. There are 3 spheres. We can glue 3 spheres together. Then because they have this shared edge, the contribution from the tensor on the shared boundary actually cancel because this orientation convention. So we can remove this. Then this became a torus. So at least so the partition function on 3 spheres equal to 1, on torus also equal to 1. So that's the kind of argument to say. So therefore, because partition function equal to 1 on every orientable manifold, then we say that this group cocycle actually describe a trivial topological order. Because partition function equal to 1 on every orientable manifold, we say it's a trivial topological order. But this state is non-trivial because I have symmetry, so that's kind of SPT states. Okay. So then mathematicians have been produced this group cohomology, calculated group cohomology for all kinds of groups. So we can produce a table for the phase in different dimension and different symmetry. And now let's come to this issue of topology invariance. And so there is a question about yes, we using this group cycle to construct many models. All those models, the partition function equal to 1, so they all trivial topological order. But we think they are different phase with the symmetry. But how do you know? So they are distinct model, but it's hard to say they belong to distinct phase with the symmetry. And usually to show the system belong to distinct phase is to find some topological invariance. If a topological invariant different, means they are different in different phase. So the topological invariant is like a physical probe. Like in the crystal, we can use X-ray to probe different crystal structure. And here we need to find something like X-ray diffraction, which can probe this different SPT phase. And one idea is that to use a partition function. But the trouble is that the partition function all equal to 1. So they don't distinguish any of those models. So if using partition function on different space-time manifold, it doesn't work. Okay, they're all equal to 1. They cannot distinguish them. So therefore, there's idea first proposed by Levin and Gu, and also Janet and I have been using a similar thing. That is, to using this, we can gauge the symmetry and consider the partition function with a gauged with the symmetry. Basically, is that if the system have a symmetry, and you can, I won't describe it. I won't go into detail. You can gauge the symmetry, and to give a space-time a flat connection. So therefore, this symmetry twist is described by some kind of gauge field, which usually is a flat connection for discrete gauge group. And so then you can evaluate the partition function of the gauged model. And this partition function is not equal to 1. And with Janet, we try to argue that this partition function probably can detect all the SPT order. So this is basically the idea. So strictly speaking, the topology invariance, this partition function with a symmetry twist give us topology invariance. But topology invariance is a little bit tricky. So the topology invariance usually given by this function. This function depends on the symmetry twist, which is exponentiation of the ratio of partition function with the symmetry twist and without symmetry twist. So with the symmetry twist or without symmetry twist, the partition function changes. So their ratio is this. It's very tempting to say, well, this term itself directly is a topological invariance. Okay, which is correct if the symmetry is if a symmetry group is a discrete. If this connection is flat. For the flat connection, I think this is correct. For the flat connection, this ratio directly gives us topological invariance. But however, for continuous group, and there you can have a non-trivial curvature, it's non-flat connection. Then things became more complicated. So this ratio itself do not directly give us topological invariance. So then the proposal is that this is different. So this kind of like a action term. The different action term are equivalent if they differ by some kind of local term. Local as a function for curvature, So there's some equivalence relation. So in general, this ratio can be a lot of functions. But if two different functions for A is the same, we said equivalent if they differ by this term, then the equivalence class of this W is a real topological invariance. So we feel that means, for the continuous gauge group, for continuous symmetry group, this may be a better definition. So in a sense, you can see from this definition, it's clear that this W is kind of like Chen-Simon theory. Chen-Simon term is such kind of term, which is non-trivial because no matter what kind of local term you can add, you can never kill the Chen-Simon term. So our Chen-Simon-like term. So the Chen-Simon-like term is something studied by Diagraph Witten, and so it turns out that this kind of a term is classified by this the integer cohomology on the classifying space in one higher dimension, which happen to be equal to the group cohomology with UN coefficient in one lower dimension. So looks like using this kind of equivalent class as topological invariance, we can detect all possible cocycles. So that's kind of an idea. So therefore, this equivalent class is our topological invariance, and so we can use this kind of topological invariance to probe different SPT order. Okay, and so certainly, let me just since I don't have much time. So certainly we can. For the UN SPT states, for example, the topological invariant will be Chen-Simon theory, basically. And we can, the different UN SPT states can be described by different topological invariants, which is a Chern-Simons term. In 1 dimension, 0 plus 1 dimension, just single A is Chern-Simons term. In the 2 plus dimension is the A times the Chern class. This is a Chern-Simons term. But there's no, so certainly in the 4 plus 1, there's also 1. But they all belong to Z class because coefficient can be any integer. And but in even dimension, in even space-time dimension, there is no such class. So basically, that gives us idea for the U1 SPT states. And because time, let me just skip all this. And so one thing I want to say that this because the bulk is a Chern-Simons theory, it's well known that Chern-Simons theory is not gauge invariant when you have a boundary. Okay. So therefore, this led to the notion that the SPT states on the bulk would produce edge theory. The edge theory would have a gauge anomaly. This is a symmetry anomaly. So there's a relation to the anomaly. But when you have this kind of understanding, then we can understand that actually this kind of group cohomology do not produce all the SPT states. And the reason is that there is also a gravitational anomaly. But the gravitational anomaly is not related to SPT state, it's related to topological order states. And the topological order states we described before without any symmetry, it also have this similar behavior, that the boundary of a topological order state have a gravitational anomaly. Okay. And but then there's a thing that with a mixed anomaly. So actually, in physics we are familiar with pure gauge anomaly, gravitational anomaly, and mixed anomaly. We are familiar with this. So actually, this group cohomology theory only describe the pure gauge anomaly, the SPT phase with pure gauge anomaly. What's missing is SPT phase with a mixed gauge gravity anomaly. Okay, so one need to generalize this to get a more general SPT phase with a mixed gauge gravity anomaly. But what is a mixed gauge gravity anomaly? Well, it's pretty simple. It's that for the pure gauge anomaly, we have the topological invariant is a pure Chern-Simons theory term like that. It's pure Chern-Simons term like that. For the topological order, the SPT, the topological invariant can be the gravitational Chern-Simons term. Oh, this kind of simple Witten class WW3 as proposed by Kapustin, and in 5 dimensions. So those kind of give us a topological order. Topological would have this kind of a pure gravity anomaly. So because those gravitational term on WW3 only depend on the SON connection of a space-time of a tangent bundle. So the purely gravity term. But this kind of term do not describe all topological order. It describes so-called invertible topological order. And so this invertible topological order is a topological order with no topological excitation. So this special kind of topological order is described by this kind of topological invariance. Okay, and then with this preparation, it's very easy to see that the mixed SPT states are simply which have a kind of a Chern-Simons term, which have a mixed gauge and gravity. So this example, there's the gauge part like U1. This Chern class is related to U1 gauge field. So that's a U1 gauge field. And this gravitational Chern-Simons term W3 is the gravity part. So this is a mixed part. So this mixed gauge topological invariance, mixed gauge gravity topological invariance would give rise to mixed SPT order. Okay. So therefore, what we did before is that we use this nonlinear model to produce. We see that the nonlinear model of this L-type theory described before can produce this kind of topological invariance. So next question is that what kind of a model, what kind of L-type theory can produce this kind of topological invariance with both gravity and the gauge connection? Yes.
If invertible topological order has no topological excitations, the implied sensing is a topological order.
It cannot be deformed to the trivial. I define the trivial topological order as a tensor with no degree freedom. There are some topological order without topological excitation which cannot be deformed into that one. So I already defined the trivial one, and so this is non-trivial in the sense they are not deformable into the trivial one.
It's like an integer quantum Hall state.
Yeah, integer quantum Hall state is that, but that's fermionic. example. Yeah. Yes.
So this statement about the 2 plus 1, this E8 cube, I mean, there is an invariant which divides the Chern-Simons. In fact, you can divide it by 6. This is Diapatodi-Singer 8 invariant.
Okay.
So they're not all, I think, given by Chern-Simons.
Yeah, there may be. So this I know you have this paper on this, so let me put it this way. I know I have a model to produce this. I mean, I have a model to produce 2 plus 1D invertible topological theory with central charge 24. I failed to produce a model to have central charge 8. Maybe it exists, but I failed to have L-type theory, L-type model to produce 8. I don't. L-type. I don't know what kind of L-type model can produce 8. Certainly, there is H-type model, Hamiltonian, can produce 8. But on the other hand, do we have a Hamiltonian producing something less than 8, as you said? There's maybe such invariant exists mathematically, but can we have a local model producing that? But at the current stage that we have a local Hamiltonian to produce E8 for H-type theory. We have a model to produce E8 cube for L-type theory, but we don't have a model to produce anything smaller. So I'm trying to say maybe these are maybe already smallest because this locality, this model have locality built in. They're built by local tensors. Yes.
Can you write the C1 omega 3 in indices? What does it look like?
What?
The C1 omega 3. How to write it?
C1 omega 3?
Yeah.
Omega 3 is this gravitational entanglement term, which is a D omega 3 is a Pontryagin class.
In this term, how would you construct indices? C1 is F.
Oh, this is F divided by 2 pi. C1 is F divided by 2 pi.
Yeah.
And I don't know what is omega 3. Omega 3 is there's a
Is it the so recipient energy?
Yeah, this certainly is a Pontryagin class, so it's kind of like ISO3 gauge field.
How can you write such a scalar? How will it look like?
No scale.
No, there are this 2 form, this is 3 form, so this is 4 form, and this is the 5-dimensional space-time. Their integration gave us action.
What happens with Lorentz with the SO3 indices? How or SO5?
All traced out, and the omega 3 order traced out. So there's a trace of some kind of a connection, let me write this way. And then there's F over 2 pi. And there's all kind of coefficient. I forgot what is the coefficient. There's okay. All these are 1 form. This is 2 form. So this is 3 form. And the total is 5 form. So the whole thing is a 5-dimensional theory defined on the 5-dimensional manifold. Huh? What?
Is it impossible to write in 2 plus 1?
2 plus no. This mixed SPT order exists. This for the U1 exists in 4 plus 1, not in 2 plus 1 dimension.
So there are no 2 plus 1 mixed SPT phases.
No. Yeah. So actually the idea is maybe you can just say. The idea is actually pretty simple. Previously we say that in the vertex we have an index in the vertex leaving so you have nonlinear single model of the group manifold. Then you can couple the group to the symmetry twist, which is the gauge field. And to produce a mixed topology order, SPT phase, we simply assume the index belong to the group, symmetry group, and the SO infinity or SON, some kind of index can be continuous, okay? And then we say that when you do symmetry twist, the symmetry twist coupled to this G index. But however, the space-time and SON connection coupled to this SON part of the index. And okay, yes, let me finish this. So therefore we can, certainly previously the different SPT states are described by different topological terms, different group cocycle. Certainly when you have this a bigger group, we also have a group. We have also group cocycle for the bigger group. Okay, that's this W is a group cocycle for bigger group, and then we couple when we choose different group cocycle for bigger group, we get a different phase. And but then after integrate the matter field, we can get a topology invariant which contain both gauge connection and the SON connection. Okay, so that's the main idea. therefore, this mixed, the pure mixed, and also the invertible topology order, using this construction, can be classified or constructed using this kind of a larger group cohomology, just G times SO. They're all there. And because the different element for G times SO is different group cocycle, give a different tensor. Okay, this different tensor can realize all different phases. Okay, so all there. But however, we cannot say the element for this one classify all these different SPT states and invertible topology order, because this correspondence is not one-to-one, but a many-to-one correspondence. We need to quotient out something. And the quotient of something is this algebraic topology part in my title, and which involving using some kind of which I just learned a few months ago, this Wu class or Stingray square, things like that, which so here we have a starting point, and then we try to quotient out something. And the reason we need to quotient out something is because this SON connection is very special. Because the thing we can couple to the system is not generic SON connection, but this SON connection always comes from the tangent bundle of a manifold. And the tangent bundle manifold is not arbitrary SON connection, they are special kind of SON connection. So we can only probe those topological environments using some special kind of topological SON connection. So that's make certain term cannot be distinguished by this special kind of SON connection. So therefore, those things cannot be distinguished, will be viewed as equivalent. So that's why you need to quotient out something. And so if you do the exercise, so this you get some table like that. So the black entry is the order result of a group cohomology of the pure symmetry group. The blue entry and the red entry is a mixed one, and the first line is a so-called invertible topological order. Okay, I will stop here. Yeah.